Yeah, thank you, Mohit, for connecting with me and requesting me for the lecture today. So, what I understood, Mohit, just confirm if it's the right assumption that I have. You want me to give a speech on the different options available in VLSI semiconductor industry. Is that right?
Yes, sir.
Okay, great, great. So, yeah, and are you all from the electronics and communication background?
Yes, sir.
Okay, great. May I ask which semester you are all studying right now?
This
Fourth.
sub yeah, second semester, sir.
Okay, so is there a mix of people like from the different years of studies?
Yes,
Yes,
sir.
sir.
There's a mix of students.
Okay, yeah. Okay, folks. So basically, Mohit asked me to give an introduction to my viewpoint on the VLSI industry, right? So the reason I wanted to speak here is that I myself am an electronics engineering background professional. I have done my electronics engineering from Mumbai University in Sardar Patel Institute of Technology. Before it was called Sardar Patel College of Engineering. Now it has changed to Sardar Patel Institute of Technology. And I had done it in a long time ago in the year 1999. So it's almost like 26 years now I have finished. And I had done my bachelor's that time. And later on, I did my part time master's in VLSI studies from MS Ramaya College of Engineering in Bangalore. And it was a, kind of a course which was done in connection with Coventry University in the UK. I guess you all are looking forward to finishing your studies and are interested to know more what happens in the industry, right? When you join the industry, am I right?
Yes, sir.
Correct. So I was, yeah. So I can share some of my experience that I have in this industry. I have a very rich experience of 25 years, and I'm in Texas Instruments in Bangalore. And I myself work in the VLSI domain as a post-silicon validation engineer, right? I was like you guys at that time in college. So the first and foremost thing is anyway the academic studies that you need to do. Yeah, you need to be really good in your academics, right? So industry is very interesting. There are a lot of things going on in the industry. There are new gadgets to work on, new technologies to work on, but everything is built upon the basics. So, and the basics, as you all know, comes from the textbooks, and the basics comes from the colleges with the help of your teachers, with the mentors that you have, and so on. So, firstly, I would encourage you all to keep an eye on the industry and try to find out what are the different domains, just as you are doing over here. But secondly, also don't underestimate the importance of having good basics and good grounding on the theory that you will be studying in the college. So be it signal or systems, be it electronic devices and circuits, be it digital signal processing, be it digital communications, and so on and so forth. All of these subjects are important. And if you focus on that in some domain or the other, you will find that whatever knowledge that you gained in the college, you will find it very useful, right? And having said that, keep an eye on the industry as well. Just as you are trying to find out more in this lecture from me, try to connect with other professionals also, and try to see what you can expect after you pass with the good grades from the college. Right. So let us get on to a little bit more information about the industry as well. So the VLSI industry, as you know, is a very much upcoming field, right? It has been there for several decades, and it will still going strong. There are so many applications in the industry for the VLSI domain in the electronics and communication background. So, in the electronics and communication field, I would be focusing more on the VLSI industry. So that because that is the kind of the advancements that are taking place the most in the industry. If you see now, there are so many companies in the offering. If you see the VLSI, for example, we have Texas Instruments in Bangalore. You have NXP Semiconductors. You have Analog Devices. You have Marvell Semiconductors. You have Intel Technologies. Just to name a few. And all of these companies are very good MNC companies, and they are working on the latest technology trends. And the work that they do is very challenging and fulfilling. And they can give you good career growth and a good prospect in the industry with a good pay as well. So you can grow professionally and financially in this field. So now, firstly, in the VLSI domain, right, as you know, so I will be just giving you a summary of the VLSI domain that these companies work on, the companies that I mentioned recently. So all these companies, what do they do? Basically, in a nutshell, they make semiconductor devices or integrated circuits to solve the real life problems. So, what are some of the real life problems? Can you help me here? Whatever you have in mind, what are some of the real life problems that we want to solve? Can anybody
How to
try?
transmit the mobile hotspot even while the laptop is sleeping, for example.
Correct. So basically related to the hotspot. Yeah, that's a good one. So hotspots, like if you have hotspots, it will let you communicate, right? It will try to get the internet connectivity, which will help in so many other different things. Any other? So another is transportation, right? We have this transportation. We want to make it affordable. We want to make it more greener. That's why we are going to electric vehicles now. So that will require batteries, and the batteries will require battery management. So that's a very big upcoming field now, where you have this power management for taking care of these huge battery systems and making them more efficient, making them more greener. Then you have communication. The need for communication is ever growing, right? The world is becoming a global village. People want to talk with each other. So now I am sitting in Bangalore, and you guys are sitting in somewhere in Kerala or Tamil Nadu, and we are talking with each other. You are able to see me. I am able to hear you all. So that is the advantage of communication, and that requires transmitters, that requires receivers. The way we transmit the messages is through the antennas, and that needs a way to drive those signals, and that is done through electronic chips. Then in a similar fashion, we have again aerospace. So now we are going to satellite communication instead of just aerial communication. So those have again the need for communication from the satellite to the earth as well, right? Then you have, for example, different applications as well, like transformers, and then you have different needs. You will have the different needs for multiplexers. Let's say whenever you design any electronic device, let's say mobile phone or laptop, right? Or you can say anything like in the industry, factory automation, right? Any industry that you go in a car, for example, manufacturing plant, in the robotics, right? In the robotics, you need a lot of hydraulic systems. You need a lot of chips to control. And now definitely everything is getting smart, right? We have smartphones, we have smart devices. So those need to computing power, and those need algorithms. Sorry, Ganesh. Yeah, so those are the different applications. So for those applications, you need the electronic devices, you need the electronic chips. We can solve the everyday problems. And as you all know, and as I'm sure you have all studied in college as well, we use the very large scale integration technology to develop these highly integrated circuits with millions of transistors fabricated on a very small area of silicon wafer. And that is able to give a huge amount of functionality and features in a very small space. So that is the advantage of the CMOS technology. So now there are different phases involved in this process, from the concept phase right up to the stage where you get the product in hand. So for example, this mobile phone, right, that I'm having with me, this is a product. Now, first, this product has so many features in that, as we all know. It has a camera, it has a display. Main thing, it has a processor that's able to carry out all these functions. It's able to have a light, LED, a torch light, right? It's able to have a SIM card, it's able to have antennas, it's able to have transmitters and receivers, and so on and so forth. So everything starts with a specification. What do you want to solve? What product you want to make, right? What is your interest, first of all? So Texas Instruments makes a lot of products in the market. It's one of the very big MNCs, multinational companies, and it focuses on power management in a big way. So if you pick up any product like this mobile phone, for example, if you open it up, so some of the chips will be from TI, Texas Instruments, for power management. And then we'll also have interfacing devices in this. For example, it has a charging port, it has a USB data transmission, it has the Bluetooth, right? And it has so many other blocks in the mobile phone. So it makes the chips for all those blocks. So first it starts with a specification. Let's say I want to design uh, a chip that's able to transmit the Wi-Fi on this phone, right? So we have a Wi-Fi on this phone, right? The first thing we need is the internet for the phone, basic need of communicating, right? With the internet. So let's say I want to make a chip, which is a Wi-Fi chip, which will be able to receive the Wi-Fi signals around, and if you're able to transmit to the hub or the host, and it will be able to download the data, it will be able to upload the data. So first you need a specification for that chip, right? So that will be the starting point in the development of the product. After you develop, right, after you know the more about the product, that this is a Wi-Fi chip, it should have a transmitter, it should have a receiver. Okay, then you go a bit more into the detail. How much should be the signal strength it will be able to transmit, right? So that will be one of the things that you will be taking care of in your design phase. So that is the design phase. First is the specification phase, and the next is the design phase. The specification phase is done by a systems engineer, right? So this job of the systems engineer is to study the market, right? As to what is the need of the customer, right? What kind of problems the normal customers, my customers, are facing. For example, the manufacturer of this phone, right? I have a OnePlus phone. So he'll be sitting with the people at OnePlus and asking them, what are the problems you are facing? And then he'll be studying the market. And then he'll be coming out with products that are better than the present products that can solve the problem. For example, if the current market chip is able to communicate, let's say 20 meters from one place to the host, and people are finding it difficult, he will design a chip that is able to communicate 30 meters. That is the improvement that he is trying to do. And that's the differentiation he's trying to bring. So again, the system engineer is again worried about first what my customers want. So he can't go over the top and let's say I will design a system that will work till 100 meters. And the customer don't want that much. Customers are interested in only 30 meter. Current chip is working to 20 meter and they want a chip till 30 meters. So there's no point in giving the specification to 100 meters. Because again, if you go to solve that problem, definitely your challenges will be different. The time that you need will be changing. The technology will need to be changing. And you're not solving the correct problem, first of all. So first, the system engineer will try to find out how to differentiate, how to add value to the market, what his or her customers are looking for. Right? So that will be done by the system engineer. Now, system engineers normally, the way they work is they talk with the customers and they have to understand the whole environment, the whole system from the starting to the end. Right? So that is one thing. Then after the system engineer finishes his specifications for the product, then he will pass it on to the design team. So next it will be picked up by the design team. The design team will say, okay, you need a gain of so and so dB. You need a transmission strength of so and so power. You need a receiver that will be able to work at let's say 20 microvolt per dB. Right? And then what they will do is they will try to design. Now it is designing phase is what you would have done also in college as well. Designing the op-amp. Op-amp is a basic building block, right? So they will take the basic building blocks and design the receiver for that, design the transmitter for that. Then again the system engineer will say, I have a limitation in that it should work in so and so power, right? Everything nowadays, many things are working on a battery system. You don't want it to take it excess power. So he has to design the circuit such that it works as low power as possible. He has to find the different topology. There'll be the architecture selection. One architecture is better in speed, one architecture is better in power. Some architectures are more area. It will take, some architectures are slower, but they take very less area. So always it is a trade-off. You might have heard this word a lot. There is always a trade-off of what you want, whether you want to have the best possible performance. Like if you pick up an Apple iPhone, they want the best user experience. They want everything should be the best quality. They don't care that much about the cost because that's not the problem they are solving. If you see the other mobile phone manufacturers, for them, they want to address the mass market. They know that the people need to afford their phone first to use it. So they want to sacrifice the features and focus on the features that are basics, minimum features, which the customers really want. They're willing to pay for it. And the quality they can little bit sacrifice because that market they are not addressing. So in that way, they will design the chip, and the design is what again you will be doing using the different simulation tools, like you will have cadence design softwares, right? Then you have synopsis if you are doing digital design. And design also are different kinds. You have analog design to do the analog blocks, then you have digital designs to do the digital blocks. For digital designs you will need the RTL skills, register transfer language coding. For that you will need to know VHDL. Are you guys familiar with these terms? VHDL, Verilog, RTL, and so on?
Yes, sir.
Yeah, great. So these skills will come in handy when you work on design part of it. Yes, Sarvesh. These things you will learn later on as well. These are quite important. So these will be used again and again in the industry. And you will also learn on simple blocks like band gap you will have to design. You'll have to work on current mirrors if you are looking at analog design. You'll work on logic gates, how to design the AND gate, NAND gate, and those kind of library IO cells. Then you'll also work on ESD, for example. ESD is a big domain in VLSI. Does anybody know why ESD is important?
To preserve the circuit from being damaged, as instruments are very sensitive when we are dealing with higher data.
Yeah, Jaya, Raj, sure. No problem, Pamu. So as Jaya said, we have static electricity everywhere around us. So whenever I'm rubbing my hand with my clothes, I'm generating static. What happens is this is an insulator. So whenever the charges are generated, these charges are not able to go anywhere because insulators don't conduct. So whenever then I touch anything like this mobile phone, for example, when I touch, so these charges travel from my hand, from my clothes, wherever, and it goes to the mobile phone. And if, for example, the mobile phone is grounded, for example, right, is connected to the earth in some way. Let's say I'm charging it over here, and my charger is connected to the power port, and that is earthed. So then it finds a path, and these charges flow through that. And then if it goes through any integrated circuits, those charges can go as high as 2000 volts. They go for very less time. They don't have that much energy, but the voltage is very high, even though for a small time. So that is able to disrupt all the, it is able to damage the electronic circuits. And that is able to damage the circuits and it will destroy this phone. So to prevent that, you always put the protection on the chips, and that is called as the ESD protection. Basically, these are diodes. These are diodes that whenever that a huge spike comes, those diodes turn on, and that takes all the excess current and it prevents the voltage from going high. Because when the diode conducts, it will clamp the voltage, right? The forward bias voltage. So the voltage won't be able to going that high, and that will preserve the integrated circuits. So some people will work on these ESD blocks, and then they will put all these different blocks together. They will be then again simulating at the top level. So once they will simulate at the top level, and then they will run the simulation, and there will be the analog simulations running, there will be the digital simulations running. Each person, like it's a big team of people working, there'll be like 15-20 people. Some will be on the digital design, some folks will be on the analog design, right? Some people will be doing the ESD, some people will be doing the IOCell. They're independently working with each other, and then the whole thing comes together into the form of a chip, and then the whole thing gets simulated. And models are very important, right? In Cadence, whenever you simulate a schematic and you connect the different transistors and the different diodes and the different components together, those needs the models. And those models you'll get from the fabrication house. So fabrication house is the factory in which the semiconductor devices will be made with the process of photolithography. You would have all known about this process, right? Have you studied about CMOS fabrication yet?
No, sir.
Okay, so that's a very important topic, CMOS fabrication. It's good even if you if you get a chance, just search online for how a CMOS chip is fabricated. It's a very eye-opening process, and it's a very highly advanced process. And you would have studied how a transistor is made, right? You have a source, you have a drain, then you have a gate, and then you have a connections to the different transistors, right? So just see that online. So that is made in a fabrication plant. Now this is the technology is very highly advanced. Nowadays, it used to be in micrometer at which it was fabricated. Then it goes on reducing in the size because people want to add more functionality. So they want more transistors, but they don't have space. So what do? They make the transistors smaller and smaller and smaller. So right now, as you might be knowing, people are able to make a transistor that is 2 or 3 nanometer in length. And what is a nanometer? 1 micrometer is 1 millionth of a meter. And 1 nanometer is 1 billionth of a meter. So you can imagine how tiny and small it is. And you can imagine how the billions and millions of transistors are fabricated onto a small chip. So who will tell how the transistor will work? Simulation tool doesn't know, right? What is the quality of the transistor? The process engineer who is working in the fabrication house, he is designing that process. He is working on the machines that are fabricating the chip, and he will characterize that IV curve for the transistor. You would have come across that. IV curve is always very important in any electronic component, right? So he will give that IV curve, the current voltage characteristic, to the designer, that this is how my transistor will look. And he will take that and he will put that as a model in the simulation tool, in the Cadence or in the Spice or LT Spice or P Spice or Synopsys or whatever. And they will take it and then they will have a huge netlist. And that netlist is then solved by the simulation tool, and then it will show how well the circuit is working, if the circuit needs any adjustments. Finally, the design team will do a lot of analysis. For example, if it's an analog circuit, right? They will see the stability analysis, whether the amplifier is stable or not. They will see how much gain you are getting. They will see the settling time, how much you are able to get, right? So these are the different fields that you'll come across in the design domain. This is a very big domain in any VLSI company. And the design domain is divided into digital design, analog design. And there is another third kind of design which is called as mixed signal design. Mixed signal design is a combination of analog and digital both. It has a bit of analog, you need to know the analog basics, and it has a bit of digital, not too much, but a bit of digital. For example, if you would have heard about circuits like analog to digital converters, digital to analog converters, right? For example, this microphone that I am speaking on, it's a analog to digital converter, right? My voice is analog, it's sensing it, and then it gets converted into digital. So it's a analog to digital converter. This headphone that I'm wearing, right? So it's a digital to analog converter DAC. So it's taking the digital signal, making it analog, and then giving it to the speaker. So analog to digital and digital to analog converters are mixed signal devices. It's a very big field in VLSI because everything is getting digitized and the world around us is analog. Therefore, we need to convert those analog signals to digital. And then whenever we give it back to the user, we need to convert it from the digital to the analog signal. Okay, is it making sense so far? Okay, that's great. So what kind of skills do you need for a design engineer? Definitely, you need a lot of basic skills. Like you need RC circuits, right? You need to understand your electronic devices. You need to understand electromagnetic theory also, right? Because a semiconductor device is made up of charges, right? Positive, negative charges, how the charges flow and all. It's all electromagnetics, right? Charge distribution and voltages, and currents. So the basics of all that is electromagnetics, right? So these will be important for you guys to become better designers, either analog or digital. Now, how do you choose which domain you get into? So again, some of these companies like Texas Instruments, right, or any big company like say NXP, Qualcomm, or Google, or whatever. So they hire based on their need. For example, if the hiring manager might need a digital engineer, so he'll come to the college and he'll hire for a digital engineer, right? So you get to work on the digital domain. But let's say you will also get a chance later on in your career. Let's say after 4 months, 6 months, or 1 year, after you are a bit settled in the company, you can always have your conversation with your manager. Let's say I'm more interested in analog, I'm more interested in mixed signal, or you might be interested in digital, whatever, right? So then you can have the conversations with your manager. And these companies have a very good work culture, the MNCs, right? They want, nowadays they want you to work in whatever you want to work in. Even if I want digital engineer, right? Let's say you are a good engineer, but you want to work in analog. But I will be supportive of that. I won't say, no, no, you have to work in this. Those days are gone actually. People value talent because they know that you all have an option, right? There are other companies also. If I say no to you, you will go somewhere else. So better, okay, if you want to work in analog, let's say, okay, I don't have that opening. I'll talk to my colleague in some other department where he has that opening and I will place you there. I don't want to lose you. So don't worry that much about which domain uh, is a good one, which domain I should target, which domain has scope. All the domains have scope. Take it from me. I have spent 25 years in this industry. I know people who have become very successful in each and every domain. There have been people who have joined design engineers, they are successful. There have been people who have joined as validation engineers. So now I am validation engineer in Texas Instruments. I'll tell a bit more about my role also, but in short, my role is to make sure that whatever the design team has designed, after the chip comes back out from the factory as a product, I have to make sure that it is working as intended. So design team would have designed it for the specifications that the system engineer has given, right? But I have to make sure that it really works like that in the laboratory. I will use real world instruments. I will use real world environment and prove that the chip works or it doesn't work. That's the job of a validation engineer. So I have seen people who have been very successful validation engineers in a very short span of time, let's say 7 to 10 years, they have become very successful. I have seen very good layout engineers. So this domain I have not touched. What are layout engineers? So what happens is once the design engineer, right, just to expand a bit more on what is a layout engineer, the design team designs everything in the schematic, right? But finally it has to be fabricated. So the layout engineer, what he or she does is they take the schematic and they put it in their tool, whichever tool they are using, let's say Cadence, and they place these different transistors in the appropriate places and they put the connections between those transistors and they fabricate the whole chip as a realizable chip. And that layout, so layout is, if I try to explain you, a layout is they take that building blocks, like assume those are the Lego blocks. They take all those blocks from the schematic and then they place it and they put the connections in the form of a physical product. So design engineer will have just a schematic with him, but a layout engineer will take those blocks and then they will connect those components together to be able to fabricate that chip in the fabrication house that I was mentioning earlier. So there will be different formats for that. It's basically mechanical 3D formats. Like you might have heard about a format called Gerber file, for example. Gerber file is a very common industry format for these PCB boards, these printed circuit boards. So those are all fabricated using tools, right, in the factories. So how do they know how to make the board? It's a format. So it has the different X and Y dimensions that you etch a line from this point to that point. You connect this transistor from here to there and so on, right? So in the same way, the fabrication house will take that format for that file, whichever the layout engineer gives, and he'll be able to fabricate that. So that layout engineer also will take that design and he will work on the tools and he will produce that layout for the designer. So So that is one another domain in the VLSI industry, layout engineer. You can search for that as well. And then some different domain. There is a qualification engineer. So who is a qualification engineer? So these chips that we fabricate, right, in the fabrication plant, we need to make sure that they are good quality. Now, how do I ensure? What do I mean by good quality? It has to work for, does it need to work for 1 month? 2 months, do you say it's good quality? 3 months, do you say it's good quality? If I say a car, for example, something like a car, people can be using it for years and years, like 20 years also. So the components in that car should be able to work fine as intended for a duration of 20 years. So that much quality should be there. So the purpose of a quality engineer is to make sure that the design, whatever the design engineer has done, and whatever the chip that has come back from the fabrication plant is able to survive that much time in the field. By the field, I mean in the real application use case. And how do they do it? They put the chip in a very stressed environment. Now, obviously, nobody can wait for 20 years, right, to know whether the chip is good or not. He won't have that luxury of time to just wait for 20 years and say whether it's working till 20 years. So, how does he do that? He stresses the chip so much such that it becomes accelerated lifetime testing. I'm not sure if you have heard about the bathtub curve. A bathtub curve is predicts the quality basically. So the chip is like a bathtub. The rate of failure of any system, right? So a chip like a bathtub is very high in its early life. Then after a certain duration, it becomes steady, it becomes like a flat. And then when it reaches a certain age, again the rate of failure increases. It becomes like a U-shaped, kind of a U-shaped and bit of a flat, and then again rises like that. So it becomes like a shape of a bathtub curve. So basically, that is another branch in VLSI. It's called reliability engineering. So the quality engineer or the reliability engineer has to make sure that the quality is good enough so that it works for the intended lifespan. And for most commonly, the intended lifespan for devices which are not life critical is like 10 years. So for 10 years, if the chip works, they'll be able to say it's a good quality. So what do? They take these chips and put in an oven. So oven will be working at, let's say, 100 degrees, 120 degrees, 150 degrees, and so on, depending on how much stress they want to give. They will take the voltage higher. Let's say the voltage it needs to work is 3 volts. They'll take it 9 volts, 10 volts, just to simulate the accelerated aging. And then they will remove it after, let's say, 1,000 hours, and they will test the chip. If the chip is able to survive that, that means it's an indication that it will be able to survive the entire duration of its lifetime. So that is reliability engineering. And then there is a validation engineer, like how I explained right before. So what we do, I have been a validation engineer most part of my life. So what we do is we don't uh, do any assumptions whether this chip will work or not. The design engineer may be the best engineer, but problems can happen from that place that we can't imagine. So I take that chip, then I will put it on a board. I'll have an application board. Any chip will need a board, right? It can't work in thin air, right? This phone, if I open up, there'll be a PCB, printed circuit board inside. So I will, my chip also will need a board. So first I need to design a board for that first to check, test it. Now that board design again is having its own cycle. First I have to make a schematic for that. Then I have to do the layout for that also. Then again it goes to the fabrication house. Then I get the board back. Then I need to make sure that I have the ability to connect all the instruments together on the board, right? So I want to check the bandwidth of one amplifier. So bandwidth, as you know, it's the ability of the amplifier to pass the frequency of the different frequencies. So normally, so Harshvandan is asking me something. Uh, yeah, the total amount of times we can cycle a component, right? Yeah. So that is again related with the quality, right, Harshvardhan? So that again is part of the test system. So they will be doing this multiple charging, discharging, right? But again, each and every battery might not go through that. They might have like one lot of, let's say, 1,000 batteries. They'll take one or two batteries from there, and then they will cycle it for 2,000 times. And if it passes, then the whole lot is released. If it doesn't pass, then that lot is not able to move forward. They have to again see why these two batteries are failing. They will again test it. They will again see what's going on. They'll pick up some more batteries from that lot, and so on. So that is again the job of the production line, basically. After the product is released to the market, it comes into the picture. So there are two phases. One is before you release the product to the market, you make sure that product is working fine, design is working fine, everything is okay. Then you release to the market. So once you release to the market, right, then the production line will also do the different kind of tests on the product, and that is the once those tests are passing, then only that product is able to go to the market. And then yeah, Sarvesh is asking about the verification, right? What are the different kind of verification? So first is the pre-silicon verification. Okay, that is done by the design team. That is all based on simulation and the modeling. So first, whenever I design something, I will think it's working fine, but it has to work under all the scenarios. So that scenarios can be different power supply ramp ups, for example, right? It can be different temperatures, for example. It can be different kind of test cases which the customer has given. So that is a verification. Also, it has to go through. Then this is the post-silicon verification. After you get the product in the lab, that verification is again the post-silicon verification that validation engineer like myself will do in the lab. Then there is also a test engineer. So what is the difference between test engineer and validation engineer? Let me try to explain. Basically, test engineer and validation engineer both have a very similar role to make sure that the chip is working correctly. But a validation engineer has a little bit more focused approach. He will zoom bit more into the device, right? And make sure that the device is not able to break under any conditions that matters. So I will be cycling the temperature. I will be testing hot temperature, cold temperature, room temperature, any temperature in between. I'll be testing at different voltages, low voltage, middle voltage, high voltage, and making sure it's fine at all of those points. Then I will be taking different cases that the chip has to work in, whether it's able to meet the transient cases, for example. Let's say if sudden spike in the activity happens, I'm using the camera in my phone, for example. Suddenly inrush current came, battery voltage dropped, whether my chip is able to work in that case or not. So I will be taking my chip in the lab and I'll be connecting all sorts of different instruments. So some of the instruments that I connect is the oscilloscope, for example. Then I select a power supply, for example. Then I connect electronic load, for example. I connect a vector network analyzer, frequency. The instruments also have different kinds of domains, as you might have studied, right? One is a time domain, like oscilloscope. One is a frequency domain, like the spectrum analyzer. I will connect all of these different things, right? Different kind of instruments, and make sure that the chip works. And only if the chip works in all cases, I'll be releasing it to the market. So that is the verification, Sarvesh. And yeah, and the reasons facing it in the semiconductor industry in India. Yeah, that is a good question, Mohammed. The reason that we are facing a struggle in the semiconductor industry in India, right? Because see, firstly, it is a very technologically advanced sector. If you compare the semiconductor industry to the software industry, I can say software anybody can learn very easily. If you give me a computer, a laptop, and if you give me 1 year, I can learn many programming languages and I'll be able to make a website. But in a semiconductor industry, it needs a lot of more hard work and lot of more theory. I need to break my head into how the electronic devices work, first of all. I need to understand the different simulation environments. I need to understand the theory of it. I need to work hard on that. And finally, even if I do all of these things, I need to test it in the lab. For that, I need different instruments. The instruments are costly. That needs a lot of investment. And these fabrication plants that I was saying earlier, right? I need them to make my chip. And those are very complicated factories. The machines have to work at nanometer levels. So not many countries, even India, has a very few fabrication houses, right? As you might be knowing. There are some government institutions that have fabrication houses, but those are very basic ones compared to the high tech ones. Those work in the micrometer level, whereas currently we are working in the nanometer level. So that's the reason semiconductor industry, the number of people in the semiconductor industry are less, but whoever are there, and if you focus, if you kind of try to learn the trick of the trade, you try to have good basics. If you work hard, then you can grow a lot in the semiconductor industry. So definitely, India has a very bright future in the semiconductor industry, but that will need patience also. That will need hard work. You will need a good grades. You will need to some. In some cases, you might not be able to just do with a bachelor education. I need to go higher studies also. Need a good internship projects and so on. So yeah. So if you see, those are the different domains, right, that I was speaking, that are available in the semiconductor industry. And then the one domain that I kind of briefly touched upon is a test engineer. So what does a test engineer do? The test engineer also does the testing of the product, but the testing that he does is on a highly automated setup. Because every chip that goes out from Texas Instruments, let's say, into the market has to be guaranteed to be working. And how it can guarantee that it's working? We have to test it that it's working. And how can we test it that it's working? One is the validation engineer that I told, that he will make sure that a chip works. But he will not make sure that each and every chip works. He will make sure that the design works. But once the design is released to the market, then it's the job of the test engineer to write a test program. He will write a test program that runs on a very automated test setup, which will be running each and every chip that's coming out of Texas Instruments. It's running that and it's going into the market. And that once it passes that test program, only we are able to sell it in the market. So that's the job of the test engineer, to write a test program that will be able to test the chip in a very short amount of time. We don't have the liberty to spend hours and hours on test. It will test the chip in, let's say, 10 seconds or even lesser, sometimes 2 seconds, and sometimes even in milliseconds if it's a very small chip. And that chip then goes out into the market. And that is the job of the test engineer. Layout engineer, I told, right, that he will do the different layouts on the chip. Then you also have something like a firmware engineer. So you have so in the skill set, if you talk about, yeah, generally see artificial intelligence is coming up in a big way. As you all know that it is a new, very emerging field, and the way it's trying to penetrate everything. Some of it is hype, but if you ask me, it's very real. The computing power that they are putting nowadays is able to solve problems in a very quick manner, right? And especially the routine tasks that people do, the very basic tasks that engineers do, those are able to be done in a very quick and efficient way. For example, I would compare that, right? If you have a calculator, for example, calculator also is a computer, right? And I'm able to calculate some stuff on there. So compare it to a laptop, right? It's a kind of another level. So a laptop can do everything what a calculator can do. Plus, it can do so many things more, right? So artificial intelligence again is able to be a very good tool for me, but it won't be able to take my job, is what I think, because I will always be better than artificial intelligence, right? See, if I ask artificial intelligence, right, to write a piece of code, right, it will write it for me. To design a circuit, it will design it for me. But basically, I will have to make sure that it's good enough, right? I'll have to be more smarter than the AI in many ways. I can't just release whatever the AI gives, like whatever Gemini gives or Claude gives. I can't put it into the market. There'll be so many mistakes in that. AI also is not perfect. I'll have to make sure I'll use AI as a tool, just as I use a laptop as a tool. I use calculator as a tool, but I never get rid of my brain, right? In the same way, AI is like a tool that I'll be using. Now I have to be good at it, obviously. I can't say I'm enough. AI is less than me. I have to acknowledge its power. So if I have a laptop, I have to learn Windows, right? I have to learn the tips and tricks of Windows. Otherwise, I'll be behind compared to a person who knows how to use a laptop, who knows how to use Word, Excel, and all. So I have to learn that. In the same way, I have to learn AI also. I need not be scared by AI. If I learn artificial intelligence, then I will use it as a tool, like a laptop or computer or whatever, like a mobile phone. I'll use it and I'll become a better engineer. Maybe some jobs are taken away by AI, but in my view, that's a good thing because those jobs are the basic ones that nobody likes to do. For example, if it's writing a simple piece of code, why do I want to write a simple piece of code if the AI can write it for me? I'll work on some better project. I'll work on something that has a better impact, right? So skill wise, I think nobody can be a good engineer or a good software engineer or hardware engineer just by being tech savvy. So just by knowing what all is going in the industry, it will get you a few points. It will get you a few brownie points. But it will never be comparable to an engineer who knows his basics, who knows how the RC circuit works, who knows what's a good amplifier, who knows his Kirchhoff's voltage law, Kirchhoff's current law. That's why in any interview that you go in the industry, they won't ask you about AI. They won't ask you how much AI you know because they know that this thing can be learned later on. If you have a good basics, if you have a good basics and you appreciate what's a good electronics engineering practice, you can always learn about AI. You can always learn about other things. But if you don't know how the RC circuit works, and then you start going on the AI and asking how to make a band pass filter from a RC circuit, how will you be able to differentiate between multiple RC circuits? How will you be able to differentiate if something doesn't work, how to fix it? AI can't do everything for you. It can help you. And what it cannot do is your intelligence. That's a God given intelligence nobody can match. AI also human being only has made, right? So that is the main thing. Keep your basics in mind, right? And after the basics, yeah, use as many tools as possible. Use AI, use forums, go to these seminars, webinars, and so on and so forth. Yeah, similar thing for that physical design. Also, I was saying, right? See, many things will be impacted by AI. Many things will be automated, but that doesn't mean a layout engineer will vanish. Nobody needs layout engineer. We won't see all robots working in the factory because as AI will do that thing for us, some new domains will come up. Something that was not even possible before will open up. That will be needing those engineers now, right? So definitely. So this is the now almost we are 1 hour now. So now, so I won't take up too much of your time. So I will just summarize um, a bit. So yeah, Mohammed. So you are asking how to become academically strong in VLSI, right? So just focus on your academics also. Just sit with your books. There are a lot of videos and stuff nowadays. Don't get too much distracted by a lot of other different videos, but there are good people to follow. There are some very good channels. So follow those channels which focus on the theory, the theoretical background, the analytical skills, debugging skills, and then follow those channels. Get good marks in your college. If you get good marks in your college, that is a very good indication that you have done a good job in mastering your basics. Okay, those are the things. So just to wrap up, very large scale integrated integration is a very upcoming domain in electronics. There are a lot of opportunities in India. Many companies exist in Bangalore. There are many companies in Noida, Delhi, some companies in Chennai as well, a fewer companies in Mumbai, Pune, and so on. So I would say that the headquarter is Bangalore. If you and a bit second might be Noida, Delhi. And the way to what are the good pointers to become successful in this field? Just be good with your basics. Be in love with your books. Ask a lot of questions to your teachers. Do a good job in projects. Yeah, internships is a very good field that you want to do. If you get good internships, please feel through. Yeah, go ahead, get good internship, do good projects. At the same time, yeah, learn as much as possible. Keep an eye on the industry, but try to finish your academics with good grades. I would say that is the best first thing that you should do. And secondly, don't worry a lot whether this field has scope or not. You can take it from me. It's a very good field. It has a very good scope. So, and in that also there are different domains that I explained you. There is a systems engineer, there's an analog design, there's a digital design, there's a mixed signal design, there is a validation engineer, there's a test engineer, there's a quality and reliability engineer, there's a product engineer, and so on. And with that, I would conclude and let open it up for questions if anybody has. Um, I will just take first one question from Harsha. Um, yeah, actually, these jobs will be in a risk, Harsha. But that's the reason why we need good people. That's I would view it as an opportunity rather than a threat. So that's a kind of an opportunity to get good at your skills, so that even if you have AI, people will want you as compared to somebody else. Right? So if anybody has any questions, I can take it up. And okay, so that's all from my side, Mohit. I hope you enjoyed this lecture. I enjoyed it. Thank you, everyone. It was great to have you all. Thanks, Mohammed.
Thank you, sir.
Sir,
You're
I
most
think
welcome.
there are a few more questions in the chat, or is it over?
Yeah, there are a couple of questions. Yeah, the grades matter, Harsha. Grades definitely matter because those are the indication how well you have grasped the basics. And what are the basic concepts to learn to get into top MNCs? Yeah, all your subjects. So all your subjects. So I would not, because as I said, there are so many domains in VLSI, right? Digital domain, digital concepts are important. Analog domain, analog concepts are important. So you will need electronic skills, right? Electronic devices and circuits. You will need signal processing. You will need computing. Software is coming up. Software is there everywhere. You need Python programming and so on. So all those basic concepts will be useful. Okay, so with that, I wish every one of you all the best in your studies.
Thank you, sir. I think we have come to the end of this session. It is my privilege to deliver the vote of thanks. So, we are truly honored to have hosted Mr. Asif Surti as part of ProbeYond, our guest lecture series that aims to bridge classroom learning with real world industry practice by enabling students to interact directly with professionals shaping today's electronics industry. We extend our sincere gratitude to Mr. Asif Surti for graciously accepting our invitation and for sharing his valuable insights on post silicon validation. Sir, your session offered our students a clear and practical understanding of a critical yet often underexplored stage of the VLSI lifecycle, where designs are tested against real silicon and real world constraints. The way you connected theoretical concepts with industry level responsibility and problem solving made the session both engaging and deeply insightful. Finally, we thank all the participants for their active presence and thoughtful questions. Your enthusiasm and engagement made the session truly meaningful. On behalf of the entire ProbeYond family, I once again extend our heartfelt thanks to Mr. Asif Surti and to everyone present here today. Thank you so much.
Thank you very much. I think I'll just quickly cover one question from Akash, which I was not able to answer. What skills apart from academics? Skills apart from academics, Akash, yeah, try to keep an eye on programming also. Electronics also needs a lot of programming. Python programming would be useful. Try to really understand the stuff. Go through the YouTube videos because there's so many things in DSP also. Try to understand what's the importance of Fourier transform. Try to understand exactly what goes wrong, when the stability is not met and so on. Okay. Yeah, thank you so much, Junaid. Um, and I wish everyone thanks for attending the lecture, and I wish everyone all the best. And you can keep me in touch if you need anything. Just feel free to pop me a message on LinkedIn or something like that. Thank you,
Thank you so much,
everyone.
sir. Yeah.
Thank you, sir.
Thank you, Junaid. Thank you, Mohit. Bye. I'll leave the meeting now.
Sure. Thank you, sir.
Thank you.